if you're not, just a reminder, it's being recorded. We're delighted to have Antonio Bento here with us today. He's a professor at the Sol Price School of Public Policy and within the Department of Economics at the University of Southern California. And he's going to be talking to us today about his recent research, kind of building on his research agenda, really looking at kind of climate change and adaptation to it with kind of a unifying approach, which allows identification of both kind of impacts of climate shocks, but also the impact of climate trends. So with that, I'll stop sharing and hand over to you, Antonio.
Okay. First of all, thank you very much for the invitation. It's a great pleasure to be with you guys on your afternoon and my early morning here in California. This is joint work with Noah Miller, who is a PhD student of mine here at USC, Marine Morkaji, who was former student of mine from Cornell, and Netzer Severnini from Carnegie Mellon. And just as a way to motivate the work, we recognize that failure to advance with comprehensive mitigation strategies has put more and more pressure for one to think about adaptation strategies. And in fact, as we look around the world, and in particular, as we look at the behavior of local governments, I can take my own here in Los Angeles. There's been an array of adaptation strategies that have really been quite interesting. Now, what this paper is trying to do, though, is to look at the econometrics and the methods for measuring climate impacts and adaptation, with the attempt of providing a unifying framework. And in a second, you will understand what I mean by a unifying framework. And so the goal here is to measure in a single equation both the unexpected climate shocks as well as the long-term trends. And we are going to do that by building on two old and rather well-established literatures. The first one from Macro, that really inspired by the work of Robert Lucas, has really pointed to this idea of separating unintended shocks from expected long-term trends on the economy. The exact same point was actually made in the labor economics literature by Solon in his famous 92 paper, where he looks at transitory versus permanent shocks in income. And then I'm actually going to rely on a theorem that I believe we teach to all our students in econometrics that has to do with decomposition, and in fact the properties of the Frisch-Wall-Lower theorem to really get at the implementation. Now, the application of the study, I also think it's particularly important because we will be looking at the impacts of climate change on ambient ozone concentrations here in the United States. And as you know, this is quite relevant because despite much attempts by both the federal and local governments to reduce ozone emissions and its precursors, what we have typically seen is we have had a massive success in reducing NOx emissions, but in part because of the complications of reducing VOCs, the other precursor, ozone levels have not been reducing as much as we would like. And in some metropolitan areas, as it is the case here in Los Angeles, ozone is actually on the rise in the past few years. And in fact, we would probably attribute that increase at least in part due to what we will be calling a climate penalty on ozone. So let me start very quickly by highlight the contribution of the paper by reminding you that there's really two major strands of the literature when it comes to the empirical measurement of climate impacts and climate adaptation. The earlier literature built on cross-sectional approaches with the famous paper by Mendelssohn, Nordhaus, and Shaw, and then follow-up work by Schlenker, Hahnemann, and Fischer, really looked at these permanent anticipated components of meteorological conditions. And so, in other words, the combined effect. But of course, the major problem here is that these studies suffer from the standard omitted variable biases that you have in cross-sectional studies. So while you can argue that the attempt of the study in its spirit was to capture climate impacts inclusive of adaptation, you may be wondering how much you should trust the estimates given this fairly standard problem of omitted variable biases. Now, a more recent literature attempts to get at this problem, but doesn't do it quietly, because through the panel fixed effects approaches, and here Deschênes and Greenstone, but also actually Schlenker and Roberts have made major contributions, what you try to capture is really the transitory or unanticipated weather shocks. And so you could argue that you deal with the omitted variable biases that you had in the traditional cross-sectional studies, but now you have an interpretation problem, so to speak, because the identification of climate effects are by using weather are potentially rather not trivial. And so what you're really getting here is the unexpected weather shocks. And so you could argue that you have really not accounted for the potential of adaptation. Now, in a nutshell, I think what I just said is that you could argue that the cross-section studies, at least in spirit, were inclusive of adaptation, while the fixed effects were not. And so when it comes to measure adaptation, it's not surprising that given the methods that we had in the literature, several authors at least proposed a first cut of measuring adaptation as just taking the difference between the estimates of the fixed effects and the cross-sectional studies. And you have a series of papers by Melissa Dell and co-authors. And, you know, my only comment on this is that, of course, this is a rather intuitive and potentially theoretical sound way of measuring adaptation. But to the extent that you're still relying on the cross-sectional estimates to measure climate impacts, the measure of adaptation may likely be biased as well. Not only that, but even to think more deeply about the statistical properties of this measure, it raises a series of challenges. So what we are going to do instead is to try to bring the insights of these two approaches and attempt to combine them in what I would call a unifying approach. And so to do that, we really rely on two quite simple insights, if you think about it. The first one is the idea that we could take meteorological variables and really decompose them in long-run trends and unexpected weather shocks. Of course, the challenge here is really how you do the decomposition and whether you agree with the simple decomposition that I will present you in a second. I will then do a lot of robustness checks around that decomposition to convince you that I think it's okay. But certainly, you could argue that the econometrician has some discretion here. But then most importantly, I think the minute you start reflecting on the properties of the Frischwald-Lowe theorem as it could be applied in the context of the problem here, what you could immediately realize is that we may have sufficient variation that allows us to capture both the response of weather shocks and longer-term climatic changes in the same estimation equation. And if you could do that, or at least if you could do as close as an approximation to the ideal experiment that would allow you to design that estimation, you would not only solve the omitted variable biases problems of cross-sectional studies, but indeed you would actually recover a measure of adaptation directly from these jointly estimated effects of weather and climate. And to me, that offers these three main advantages in relation to the literature, which is when you estimate the effects jointly, you have a straightforward statistical test for the significance of adaptation. But then there is something else that is linked to the traditional Lucas critique, which is, I think, and I hope to convince you that when you attempt to do this in the proposed unified strategy, you could actually identify adaptation by providing a direct comparison of how economic agents in the same location respond to weather shocks and climatic changes. And I actually think this is quite important because if you look at the literature, you often have to make assumptions about preferences of individuals in different locations to really get at these effects. So to a certain extent, we avoid having to make those assumptions. And I think that is quite important. So what I'm going to do in the first part of the talk is to give you an overview of the previous methods as a mechanism to motivate the proposed approach. And I'm going to do that in respectful of the application. And this is because at least what I would like to accomplish with this paper is, even if you don't like the application for one reason or another, I still think that there is value in learning about the proposed methodology. And so the first part of the seminar is going to be more kind of an econometric seminar where we're going to go through the nitty-gritty of the econometric approach in a general setting. And then in the second part, then we will get into the ozone formation. And I think as we do that, I will remind you of who the economic agents are in the context of our application and what is that they are doing that will trigger these types of effects. I will then jump quickly into findings and we will see where we are by the hour. So when we look at the two traditional approaches, you can immediately see that the problem with the cross-sectional approach here represented in the first equation is just the standard omitted variable biases here denoted by CI. And so if there was no such bias, the coefficient of interest would be a beta cross-section, which would measure the long-term impacts of climate on the outcome variable y. And you can see in contrast, when you move towards the panel fixed effects, you are now looking at deviations from these average of xi, and so what you're really identifying the fixed effects is across these unexpected variations of xi. And so if you take the panel equation and you difference it out, you will immediately see what the source of the variation is. You can also see that the CI drops as in any panel model, solving the cross-sectional identification issue, but then you are left with a problem, which is the interpretation of the coefficient of interest here from the fixed effects really captures only the unexpected shocks. And so what we would like to do somehow would be to combine these two approaches in a single estimation equation so that you could then know what's the magnitude of the unexpected shock, what is the long-term effect, and then by taking a difference of the two, you would have a sense of the magnitude of adaptation. And so absent of that, what you could certainly do, at least as a first attempt of getting adaptation, is you could have two separate equations that you estimate. In the first one, you basically pooled all the time series together and you estimate the cross-sectional long-term effect, and then you difference out the fixed effects coefficient from the cross-sectional one, and you get the proposed measure of adaptation as it proposed by Dell et al. And so in an ideal world, what we would like to do instead, if we could, would be to think about how you could get both the unexpected shocks and long-term trends estimated off the same equation. And so here, the ideal equation would just, in fact, be the sum of the previous two. And you can immediately see what's the econometric challenge. The econometric challenge is that the two terms here highlighted in the red box would be collinear, partly because of the way we've defined the shocks, XIT, as deviations from their mean. And so you wouldn't have a way to separate them in your ideal estimation equation. And so one way to get around that is to propose, and here you can challenge me if you don't like the approximation, is to try to do a feasible approximation to this ideal equation by, in practice, replacing the xi bar by xid. And I think this is where the interesting part of doing the weather decomposition will come in a second, which is that the D here is going to represent a longer time period over which the climate trend would vary. And so in our application, this is going to be 30 days. And so eventually what I will convince you is that you can implement these as a moving average. And when you do it, you can immediately see that you now have variation in beta C. And so you actually get fairly close to your ideal estimation equation. And if you did the decomposition correctly, per the theorem I alluded earlier, indeed, you will have all the ingredients to estimate in the same equation beta W and beta C and overcome the omitted variable biases of cross-sectional studies. So let's go one step farther. So far, I have convinced you that instead of doing these shocks XIT as deviations from their long-term mean, what I am going to do is I'm going to redefine a long-run component XID, and from there, I will measure the short-run deviations. And so the question is, how do we do that? And we do that by realizing that we can decompose weather realizations, temp, into the sum of temp C and temp W, where C here denotes the climate patterns that the economic agents gather by experiencing weather realizations over a longer period of time. And so we're going to start with the climate normal. And what we are going to do is monthly moving averages of past temperatures to create temp C. And then what we are going to do is we're going to represent the weather shocks as being revealed at the time of the realization. And those are going to be deviations of the daily temperature from the lag of this 30-year moving average. Now, if you think about how economic agents make decisions here, this is going to require adding a series of assumptions that, depending on the application, would vary. For example, in the application to ozone, given the structure of the Clean Air Act and the regulations, I am going to lag these moving averages by 1 year to basically give economic agents 1 year to adapt. You may think that this is too short of a time, and so we could do then a series of robustness checks by altering those lags. So let's understand this one step further by recognizing, again, if we take the feasible approximation that I'm proposing, and if you difference it out, and now you can see that you will be able, out of this equation, to identify both the trend and the shock, and then, of course, the measure of adaptation will come straightforward from this equation. Now, by definition, what this also immediately allows you to see is that we are leveraging the behavioral responses of the same economic agents to both the weather shock and the climatic change. And so we are not making any extrapolation of responses to weather realizations, neither over time or over space. And so I actually think that this is an important feature of thinking of the problem this way. And so, for example, if there are unobserved differences in preferences of individuals, either across time or across space, that problem would be overcome by this approach. Now, one aspect that is then quite important is to understand how we deal with fixed effects. And so here, the theta t. And remember that I've convinced you that the way I'm going to bring the weather and the climate data is by bringing a longer time series. So by the properties of the Frischwald theorem, we could actually define the fixed effects where S, as opposed to T, is defined as a longer time frame relative to the initial temporal unit of observation of T. So, for example, if T would represent days, S here could represent a season of the year. We actually are going to show you also in the appendix how sensitive the methods are to different representations of the fixed effects. And I actually would argue that in practice, the researcher will have the ability to exploit the variation here under much richer or much aggregate set of time fixed effects depending on the application. Okay, so it is important to also note that when we write our estimation equation, by the properties of the Wald theorem, we actually do not have to do long differences, as it was the case in Burke and Emmerich's paper. And so we actually are not going to create any difference. We're not going to difference the dependent variable. Right? So let me make one further point here, which is note that in the panel data approach, the time fixed effects are at the level of the temporal unit of the analysis to decisionalize the time series. Here, what we do is by decomposing the XIT into these long run and short run components, what we are going to do effectively is basically think of the variation that evolves very slowly over time. And then we do that also by including only a lower frequency time fixed effects in theta. Note that this is possible precisely because of the properties of the Frischwald-Lowe theorem. And the idea here, I'm not the greatest econometrician on earth, so I'm going to try to explain this as best as I can. But the idea is how you think of the level of saturation in the model. So the decisionalization here embedded is basically equivalent to the use of deviations in your final regression model. Now, as I said, we don't need to do the long differences approach. And in fact, we would end up keeping a lot more information in our data, because by the properties of the theorem, we could actually identify the short time shock without having to transform the outcome variable. And I actually think that this could be, again, a major appeal of the proposed method for a variety of applications where you may have more or less aggregate data of the outcome variable of interest. Okay, so I don't know if there are any questions about the method. We could proceed in two ways. Either you could ask questions about the method, or if there's still confusions about the method, hopefully some of those confusions get resolved as we move into the application. And the application here refers to the impacts of climate change on ozone. And the first thing that it's important to recognize is that you may be concerned that the economic agents whose behavior may cause adaptation is still somewhat far from the final outcome of ozone.
Antonio, can I ask a question? Because I'm a bit of a slow learner. I don't think I'm gonna catch up with you if I don't ask it. Can you go back up a couple of slides to where you have your the ideal one more, the next one up from that. So yes, the top line there is the one that we want to estimate, and you have a separate regressors, the shock and the climate. And those are separable, and that's what we'd like to be able to do.
That's right.
But then the second one, you have an approximation, but your metric for the climate here, which is the XID, the way you've constructed that by being backward looking, that XID itself is simply constructed as the last 30 or the last 10 or however many you're doing.
Yeah, that's
weather realization. So by construction, XID, it has the flavor of a bad control, right? I mean, those two regressors by construction are not independent.
Yes. So the idea here is that you're learning from the past, Those regressors are not necessarily independent. And so the econometrician has some discretion here in terms of how you construct the XID. And so what I have to convince you is that perhaps the approach is not as sensitive to that decision as you may think. And I think the argument is actually explained in some of the later slides, which is when you construct these moving averages over the past 30 years, XID is actually varying incredibly slowly, almost as if it is approximating the XI bar, right? And I think you're going to see that when I will show you a few graphs of the data where you could actually see this decomposition, and you could see what is estimated out of the traditional equations, and then what is really this XID doing. Now, there is something else that you may not like, which is we've implemented a decomposition here very much like what Solon does in his 1992 paper, which is a very simple linear decomposition. And so I will talk about that towards the end of the talk. But the point is, I'm going to have to give you a series of robustness checks related to the measurement error potentially of the shocks, given on how I define XID. Because as you correctly say, that will, by doing this construct, by default, that should impact the way I'm measuring XIT minus XID. And so let's hold on to that, and then convince ourselves that as we do, for example, different lags, or as we build this long period of time with more or less years, let's see how sensitive the results are. And I think what we're going to find out is because the XID is constructed precisely to vary very slowly over time, it turns out that econometrically you're going to see that this is not as sensitive as one may think at first when you look at the equation. I don't know if this fully answers the question, but at least I think that's my attempt at the moment.
Yeah, no, I mean, that's a perfectly fair answer. And I mean, I think it's a fantastic paper, by the way. I was reading it a couple of days ago and I came to this point. And I mean, another approach would be because clearly these two regressors are correlated because XID features in both, but it's that XIT is also a determinant of XID that gives it the bad controls flavor, as opposed to just the fact that they're correlated. And an alternative approach struck me that you could try to construct XID not using the 10 lags, but using the 10 leads, because those are then independent. You see what I mean? Maybe you're going to do that later, but then that sort of gets rid of my problem more or less. Yes. But anyway, I'm happy to be quiet.
One could do that. So the idea here is the reason why we've avoided doing that, at least so far, is because we want to put you in the mind setting that you are learning from the past. And so we didn't bring in the leads, because the minute you bring leads, there is also a question also of how you would form these future expectations of these leads. And I think that there is a standalone literature that is looking at that. But so let me convince you.
Yes, please do.
Or at least do my best of what's going to happen as we play with this decomposition.
Antonio, do you mind if I just...
And I see that there are others who have worked a lot on related topics. I see Richard Toll's head going down and up, so he's probably checking the econometric mistakes as we speak. So I look forward to his comment as well on this, because this is really, you either buy this decomposition or you don't. And so I am trying to build up the arguments one at a time in hopes that I will get as least pushback as possible. But I think that there are still some challenges in really in really nailing perfectly these arguments. So I very much welcome these questions and even potential criticisms or additional suggestions. So when we go to the application, I think what is very interesting here is the fact that ozone is an outcome that we may be interested for a variety of reasons, including the health impacts on ozone. We are interested as regulators on the impacts of ozone because despite rather costly regulations to reduce NOx emissions, given the properties of VOCs, we have not been as successful as reducing ozone, in part because you can think of the production function of ozone as being almost similar to a Leontief production function. And what is interesting is that when combined with sunlight and with temperature, these precursors are going to interact in a way that may cause additional ozone. Of course, this production function is conditional on the technology. And so you can think of a polluting facility that is choosing the levels of precursors, and the county where this polluting facility is located is regulated under the Clean Air Act. And so there's going to be constraints on regulations that are imposed by the direct regulations on NOx and VOCs. But of course, your county may end up being out of attainment, not because you have not done everything with these regulations, but because you are all of a sudden presented with a shocking temperature. And so knowing that these effects may be occurring more and more frequently, you could actually generate what we call regulation-induced adaptation, because economic agents may be adjusting for the levels of the precursors of ozone to avoid these increases in ozone that may result from higher temperature. At the same time, you could also argue that the framework is going to be general enough to capture what we would call market-driven adaptation, because over time, with declining costs in technology, those can potentially induce substitution away from these technologies that would be more intense of either or both of the precursors. So when we move into our application, what we are going to do is we are going to look at maximum ozone levels, and we are going to regress them on our measures of the decomposition of weather in shocks and trends, and then a series of additional covariates here denoted by XIT that will have similar decompositions for precipitation, as well as dummy variables for to capture the regulatory pressure that is put through the Clean Air Act, both on ozone and then in the appendix on the precursors. Z here would denote monitor fixed effects. So we have monitors for ozone and is going to be interacted with a season by year fixed effect. And this is kind of nice because it would allow us to control for differential trends by locations. And then we will also have fixed effects to capture the different allow for the different climatic regions as defined by NOAA to vary also by season and here. Okay.
Antonio,
yes.
You have now lost me. Normally we try to do these sort of things with some sort of economic indicator on the left-hand side, but you pick an atmospheric variable, which of course we try to control, so you can sort of like see it as an indirect indicator of economic activity or a human agency or something. But I'm just a bit surprised why you picked this one. And of course, the effect of temperature and of weather and climate on ozone via regulation very much depends on what exactly is that regulation. Is it a regulation for the maximum concentration in a year? Is it a regulation that holds every day? Is it a regulation on the average effect, and so on and so forth? That would determine your right-hand side.
Yes, that comment has now come by folks like yourself who appreciate the nuances of the Clean Air Act. And you may see in the revised version of the paper that we actually are going to do robustness checks of the results by looking, for example, at how the model compares when it's applied for the Northeast zone, where we had the NOx trade budget program against, for example, California, where in the summer we have the oxygenated fuel regulations precisely to regulate ozone. I want to argue that today, I'm not going to show you all those special cases, but what I'm going to show you is that by playing with different aspects of fixed effects, I'm going to implicit get at some of those issues. Now, the deeper point that you are raising, and is one that I think we're going to have to work really hard to convince referees, is that at first, ozone may appear to be a lot farther away from the economic agent that is making the decisions, as say in applications like agriculture. But again, I remind you that ozone is a result of a production function where the first two terms of the production function are direct outcomes of the economic decisions of the agent. So suppose an agent who is deciding, polluting facility, who is deciding the levels of production, and with the production comes NOx and VOCs, and the firm is actually regulated on those. So you can imagine that as the firm interacts with the county, and as the county may make plans as to what to do to comply with ozone regulations, there could be what we call induced adaptation, because you may end up putting a little bit more pressure for reducing NOx and VOCs to assure that you give yourself a little bit of space to the fact that temperature will directly affect ozone. And so to that extent, you could argue that if indeed economic agents are and regulators are recognizing this process, you actually end up getting changes in ozone that are a result of direct economic activities. Now, you could, of course, argue that this is going to be very much dependent on atmospheric conditions that are outside of the control of the agent. And this is precisely where, by giving you a lot of richness in terms of the spatial disaggregation of the estimation, one hopes that as you look at the effects in this disaggregated fashion, you actually believe that the resulting climate penalty that you are getting is mostly a result of this, is linked back with the decisions of the economic agent. Now, Richard's question is actually also important, because if you recall, in the beginning of my presentation, I said, let me first give you the general method, because I suspect that some of you may not like the application. And in several seminars, that's been the point, which people are concerned that the outcome variable may be too far from the economic agent. The reason why I still thought it was important to do it is also because I thought that by now we have learned quite a bit about the impacts of climate change on agriculture, but I could certainly apply these to agriculture or some of the other more traditional applications. And I really thought that from a public policy perspective, shedding light on this relationship between climate and ozone would be particularly useful, because We have left this literature for atmospheric scientists to often use simulation models, and by doing so, they may end up severely overestimating the climate penalty on ozone because their models are not inclusive of adaptation. And so we're going to have some trade-off here, and I'm certainly open to discuss more as to whether there are other strategies to keep convince you additionally that indeed what we are going to see here is still linked with the decisions of the economic agent. Now, to implement this equation, what we are going to do is we're going to put together a data set which is relatively straightforward, that has two main components: the weather data, that it goes back to 1950, precisely for us to be able to construct these past 30 years observations, since the ozone is going to start roughly on the 80s. And so we're going to have daily readings of maximal ozone based on the monitoring stations by the EPA, and then we are going to combine these with weather data, and then of course through the federal code of regulations, we have all the attainment status for the criteria pollutants as well, for the precursors as well as ozone. Now,
Antonio,
when we look at,
just to highlight, you've got about 15 minutes left.
Yeah,
by the way.
that's perfect.
Okay,
so I'm going to move a little bit faster. There's nothing wrong with the data when we plot the changes in average temperature. They are aligned precisely with what others have suggested, and in particular, we see roughly 0.5 degrees Celsius increase from mid-70s till about 2010. And I think to get at Anthony's question, here you can actually see what the decomposition is doing in panel A by as opposed to the fixed effects model. So it's basically creating implicitly this step function precisely because you are not doing deviations from xi bar, but rather xid. But the point is that, as you can also see, the xid will be evolving in a rather smooth fashion. Now, I want to start with the results. And so I first will present the results based on the cross-section, where we put all the data together, averaged over the entire period of 1980 to 2013. Then I will give you the fixed effects, and then I will give you the combined model. I have to say that I apologize that I'm still using the tables from my previous presentation, and the paper that I give you actually is the revised paper that I released last week. The point estimates changed a little bit, but the message is still the same. And so what we see here is that for a 1 degree Celsius increase in average max temperature, this is going to be associated with roughly an increase of 1.25 parts per billion. And when we move to our fixed effects that give us these the effect of the unexpected shocks, what we see is that a 1 degree Celsius increase in maximum temperature leads to a 1.718 increase in parts per billion in maximum ambient ozone. Now, interestingly, when we apply our unified approach, the first thing that we note is that, again, by the properties of the Frischwald theorem, the estimates on the temperature shock are actually going to be similar to the ones that you've recovered from the fixed effects approach. But interestingly enough, the effect on climate trend is actually increased by 20%. In the revised version, they are actually not all that different. The point is that you can see that if there is omitted variable bias, you can potentially correct that. Now, you can see in this table what the fixed effects are potentially doing, and then to get at Richard's point about the nuances of the regulation, in a few tables I could actually show you what happens if you change some of these fixed effects by regions to give you a little bit more a sense of the heterogeneity. And then I refer to you to the table in the appendix where you can see how robust the results are when we zoom in and compare with specific regions that have had more aggressive programs, either on the precursors, which is the NOx budget region in the Northeast, or in California with the oxygenated fuel regulations. Now, when we look at adaptation, what we see is that the implied adaptation measured by the difference between the shock and the trend is now 0.448 parts per billion. And so this immediately tells us that it shows you one of the potential problems of the fixed effects approach, which is not inclusive of adaptation. And so if you ignore adaptation, you are de facto overestimating climate penalty by more than 40%. I think this is quite interesting because, again, it hopefully allows me to get a little bit of a pass here, in a sense that even if you don't, even if you still have some concerns that the outcome variable is a little bit far from the economic agent, you can see the policy importance of actually using realized data on pollution that reflects the decisions of economic agents to estimate these effects, as opposed to construct atmospheric computational models that would not be inclusive of this adaptation, or to get the adaptation, you would require a lot more assumptions. Now, if you take the estimates that I give you here and you apply the business as usual RCP 8.5 scenario, you would get an overestimate of the climate penalty by about 0.82 by mid-century and 2.47 by the end of the century. And so I think this is economically meaningful. And of course, now to get at some of the questions that you asked me about the choices of the moving averages, and then the idea of short versus long run and lagged adaptation behavior, what we do here is we recognize that a concern regarding the decomposition that we proposed may be measurement error. And because both components are intrinsically unobserved, here we define the long run climate norm as the 30 years moving average and the weather shocks as deviations from that. So it is important to allow for different moving averages, and the point which actually echoes Solon's labor work is that the increase in the time window of the moving average effectively does the following. The permanent component of the variable that is also included in the transitory component will be less mismeasured as you increase the window. And this is exactly what we find here, even though the point estimates are actually not terribly different from one another. Let me also show you what happens when you play with the lags, because you could be concerned that we have used only 1 year lagged, and so agents may actually need more time to adapt. You could argue that this is actually quite important, because in California, we continue to have a lot of trouble, in particular here in LA, to adapt to ozone. And so we checked for the sensitivity of our results, allowing 10 and 20 years to adapt instead of 1. And I think the results are, for the most part, robust. Now, it is interesting to ask ourselves whether information that could be given to agents would alter how they respond to the shocks. And this could be a potential threat to our decomposition. And so one of the things that we did was we collected all the information on the action days for ozone, and basically, when we include that in the regression, the point is that they, again, do not alter the main effect. Neither do they alter the decomposition of the trend and the shock. Now, we played a little bit with the fixed effects, I think, to get implicitly at one of Richard's questions that have to do both with regulations, but actually equally important, about the underlying composition of precursors. So, for example, we know that there is a substantial different composition of the fleet that is on the road on weekday over weekend, in particular because of the emissions that come from freight transport. And you can see that when we played with a series of these fixed effects, again, I think for the most part, the results remain robust. And then in the new revisions, someone asked us precisely the question that Richard asked us: how do you think of the underlying regulation and how sensitive the results are to the regulation? So we have now in the revised paper results where we look at the model for the region of the NOx budget in the Northeast, and then for California alone in the months where the oxygenated fuel regulations kick in. Now, I'm running out of time. I encourage you to look at the regression, at the robustness checks, and then we can communicate offline. But there is one point about limits to adaptation that I think is important to think about. And when we look at our effects over time, what you could see is that there was a potential for quite a bit of adaptation earlier in the time period of the study, but unfortunately, I think you potentially hit a plateau rather rapidly, and these alone may also explain, at least in some parts of the US, why there's been so much difficulty in lowering the levels of ozone. I want to also link these with underlying behavior of economic agents by bringing data on beliefs for climate change and interacting both the temperature shock and the climate trend with low and high belief. And the insight that it comes here is that in places with lower belief, not surprisingly, you get a long-term climate trend effect that is 30% lower than the median counties. And so beliefs are going to be important because beliefs, in a sense, affect the interpretation of the proposed decomposition. So I am ready to conclude. Again, I want to highlight that the idea here was to propose the unified approach to measure climate change and impacts. The proposed approach relied on two major points: the decomposition of meteorological variables and the properties of the Frischwald theorem. It allows you to recover a measure of adaptation from the same estimation equation that overcomes problems of omitted variable biases, but actually more important, it doesn't rely on assumptions because you're actually comparing the responses of the same agents as opposed to have to make assumptions on preferences by comparing profiles of weather responses across space or time. I think the application to ozone, despite the fact that it is a little bit farther away from the direct agent that is making the economic decisions, as is the case with agriculture, I think it's meaningful, and it has tremendous policy implications because we really want to understand what is the magnitude of this climate penalty on ozone. And in particular, we want to understand its heterogeneity and the prospects for adaptation, whether via more stringent regulations under the Clean Air Act or whether increased technological innovation. So I would stop here. I think I'm already out of time. Is that right, Ben?
Yeah, sorry, Antonio. But thank you for an ACE talk. I guess if people have further questions, they can get in touch with you offline via email. Is that?
That is totally fine.
That's good. Great. And then that just leaves me, to once again, obviously say thank you very much to Antonio, but just to also highlight, hopefully, there we go. Yeah, it's working now. So just to also highlight, we've got 4 ACE speakers coming up that have just kind of confirmed for the continuation of this series. So we've got Amy Ando, Mar Reguan, Andreas Contalian, and John Whitehead. We're just confirming dates at the moment, but as soon as we know, we'll let you know. So yeah, and then thanks once again, Antonio.